Assalamualaikum and hi everyone. Welcome to our presentation for the Computational Fluid Dynamics project. We are Group 10 consisting of myself, Ilan Zafran bin Muhammad Zaidi, our team leader Wong Ming Hui alongside Irfan Shahni bin Razman and Muhammad Alif Najmin bin Ismail. Today we'll be discussing the effect of diffuser nozzle geometry variations on rocket engine performance and thrust characteristics. To begin with the background and theory regarding nozzle fundamentals. The optimization of a rocket engine relies heavily on the propulsion system's internal aerodynamics. To achieve this, converging diverging, nozzles are utilized to convert high pressure, high temperature gas into high velocity thrust. This entire conversion process applies the principles of isentropic expansion and compressible fluid dynamics. Diving deeper into gas dynamics, the fundamental equations define the speed of sound as A is equal to square root of gamma RT. Furthermore, density changes are directly connected to the Mach number via the momentum equation where M is equal to U over A. The physical geometry of the nozzle is governed by the critical area Mach relation, which is dA over A is equal to dV over V times M squared minus 1. This equation dictates the flow of behavior across three distinct sections. Firstly, in the converging section, where dA is less than 0, the area reduction accelerates subsonic flow, keeping the Mach number below 1. Next, at the throat, where dA is equal to 0, the flow chokes, achieving sonic velocity at exactly Mach number is equal to 1. And finally, in the diverging section, where dA is more than 0, the area increases to further accelerate the exhaust into supersonic state. Moving on to the problem statement and hypothesis. The problem is, depending on ambient pressure, non-ideal nozzle dimensions cause undesirable underexpansion or overexpansion. This geometric mismatch severely limits engine efficiency by inducing boundary layer separation and energy loss. Because of these issues, highly complex contour-exhaust relationships demand advanced methodologies like computational fluid dynamics to maximize aerodynamic efficiency. We hypothesize that by increasing the nozzle's exit diameter and length, the exhaust gas expansion ratio will increase. This variation will reduce exit pressure to ambient conditions, elevate exhaust velocities, and ultimately improve the specific impulse and thrust generation. To test our hypothesis, we established two main research objectives. Our first objective is to investigate the impact of varying diffuser nozzle diameters on exhaust velocity, flow characteristics, and overall engine efficiency using CFD simulations. Our second objective is to analyze the relationship between nozzle length variations and the resulting pressure distribution along the nozzle extension. Finally, here's a brief look at the literature review that grounds our study. To navigate this, we look at the role of CFD. As supported by the foundational work of Cheng and Chimbala, Estrada, and also Raman and the others, the Reynolds average Navier-Stokes or RANS equations are simply utilized to accurately predict surface pressure distributions and complex supersonic expansion.
Now I will present about the methodology of our project. To study the rocket nozzle, we use the ANSYS Fluent software to run it. As shown on the slide, our process is divided into 4 main steps, which is the first one is model design, followed by meshing, parameter setup, and getting the result. Running a full 3D simulation of a rocket engine is required too much computing power. So, to make our study possible with our computer hardware, we simplify the complex 3D engine into a 2D flat model. It really lowers the computer workload, but still keep our pressure data highly accurate. Using these two models allows us to easily test our variable like different nozzle size and length to see exactly how they affect the exhaust speed. Next, I will explain about the design dimension for this 3D model. Next, we move to the modeling phase using ANSYS Design Modeler. Instead of drawing the solid metal of the rocket engine, we only have modeled the empty space inside where the exhaust gas actually flow. To make sure our test was fair and to control, we kept the front part of the engine exactly the same for every test. As you can see in the first table, the inlet diameter was fixed at 1500mm and the narrow throat was locked at the 1000mm. This guarantees that the gas reaches the speed of sound right at the throat. After settling the baseline, we only changed the back part of the nozzle. Looking at the second table, we create 4 different models by changing the exit diameters. Everyone start with the exit diameter of 2236mm and we increase it step by step up to 5000mm for model 4. This specific size was chosen to let us study different flow behavior, ranging from underexpand to overexpand flow. Finally, after drawing the 2D shape, we carefully label its boundary line. We assign specific name like inlet, outlet, and nozzle wall. This labeling step is very important because it tells the software exactly where the gas enters, where it exits, and where the solid borders are. Moving on to the next step, we have the meshing setup. This is where we divide our 2D model into smaller sections so software that calculate the fluid flow. Instead of applying a basic uniform grid over the entire model, we use the specific control method that called edge sizing. As shown on the slide, we manually control the exact number of divisions for each boundary line. For example, we set 150 divisions at the inlet and 200 divisions along the top and bottom edge. We did this for a very important reason. By controlling the division, We intentionally concentrate the highest mesh density in the most critical areas, specifically around the narrow throat where the flow reaches the speed of sound. This targeted the strategy allowed us to capture the complex pressure change very accurately, without wasting our computer power on the empty exhaust space. Finally, we check the mesh quality to ensure the equation will remain mathematically stable throughout the simulation. Last but not least, we arrive at the parameter setup in axis fluid. First, we need to define our working fluid. Since our reference rocket burns refined condensate and liquid oxygen, the exhaust is extremely hot and fast. To save computer processing time and avoid calculating complex chemical reaction, we model the fluid simply as an ideal gas. This accurately captures how the gas density changes as it rapidly speeds up. Next, we set our physical boundary condition. We simulated the extreme environment of the combustion chamber by setting the inlet temperature up to 3500 Kelvin and the inlet pressure to 6.5 million Pascal. For the mathematical solver, we choose a density-based and steady-state setup, and we program the software to run exactly around 4500 iterations. Last, to properly capture the complex supersonic speed and boundary layers, we selected the realizable K-epsilon turbulence model. We also apply the second order upwind equation to guarantee a high level accuracy in our final flow result.
Starting with our under-expanded model, we observe that the nozzle axis pressure is significantly higher than the ambient pressure. Because the exhaust gas is not fully expanded within the nozzle, it continues to expand rapidly outward after exiting. This causes the characteristic blooming effect you see in the contour map. While this model achieves a high exit velocity of 2,220 meters per second, sudden radial expansions at the lip result in significant kinetic energy dissipations, and after mentioning the blooming effect, as seen in the mud animations, radiation waves at the nozzle axis are highly dynamic. The animations illustrates how this wave oscillates momentarily before settling, reflecting the transient pressure imbalance at the axis plane. Moving to the perfectly expansions model, we reach the ideal operating conditions. Here, the exit pressure is in equivalence with the ambient atmosphere. As the contour map confirms, the flow remains parallel to the nozzle axis without expansions or compressions gradients. This is the most efficient configurations for steady-state performance, allowing for maximum conversions of thermal energy into directed kinetic energy. As evidenced by our axis velocity of 2,240 meters per second, and after mentioning laminar flow, the animations confirms a rock steady flow field. You will notice an absence of any standing shock structure, which confirms the absence of wave drag and validates that our design point is perfectly matched to the ambient conditions. Next is our baseline control. With a fixed expansion ratio of 16:1, this model acts as our benchmark. The flow structure demonstrates stable developments, achieving a total thrust of 5.80 meganewtons. This design shows the best balance of attitudes performance, confirming it as the standard against which we measure the efficiency of our variations. Finally, we analyze the over-expanded model. In this case, this ambient pressure is greater than the exit pressure. This causes the surrounding atmospheres to compress the plumb inwards. You can clearly see the formations of oblique shock wave in the contour map. This internal shock and the resulting flow separations at the nozzle walls introduce servo pressure fluctuations at vibration rates, which significantly degrade overall nozzle efficiency. And after mentioning shock wave, the animation here is the most revealing. It clearly displays the standing oblique shock wave within the nozzle and the oscillating separation point on the wall. To summarize our findings, let's look at the comparative data. Our result shows that while the baseline model year-specific impulse at 229.34 seconds, the perfectly expanded model remains the most stable in terms of flow quality. In conclusion, this simulation demonstrates that optimizing steps expansion ratio is critical to minimize shock losses and maximize net thrust.
Looking at our error analysis, the slight variation between the one-dimension isentropic theory and our CFD result occur because the one-dimension math assume the uniform flow, while our 2D CFD models realistic area-weighted cross-section. Additionally, we noted the minor numerical diffusion, which slightly smooths out our sharp shock wave profile. In terms of limitations, treating the exhaust gas as an ideal gas ignore the high temperature variations and chemical dissociations. Furthermore, our 2D exit symmetric approach cannot capture the asymmetric 3D flow separations. Lastly, our steady-state adiabatic wall assumptions omitted the transient startup shock wave. To advance the research, The future studies should include a grid convergence index to eliminate the mesh dependencies and utilize the 3D transient solver and implement the real chemical reaction kinetics. In conclusion, our simulation successfully validated the area mark relationships, confirming the choke sonic conditions exactly at the nozzle throats. By expanding the exit diameter from the model 1 to the model 4, the exit gas accelerated from Mach 4.63 to Mach 5.29, effectively converting the thermal energy into the kinetic thrust. However, this expansion does not yield the infinite linear gains. Model 3 emerged as our optimum configuration, yielding the peak net thrust of 5.800 Mn and a specific impulse of 229.34 seconds. Exceeding this threshold, as seen in the Model 4, causes severe overexpansion that hurts the overall engine efficiency. So, ultimately, this framework provides a highly cost-effective tool for navigating the critical aerospace design limits. That's all from us. Thank you very much.